Um, Hi, everyone. So today we're very happy to have Lampros Lamprou from University of British Columbia giving us a talk about inside the holographic black holes. Thank you so much for accepting to give this talk and looking forward to it. Please.
All right. Well, thank you for the invitation. It's always fun to interact with you guys. So I will be presenting work that I've been doing for a couple of years now. The first installment of this work was back towards the end of 2020 in a paper with Daniel Jafferis, where we articulated an aspirational framework. And more recently, last November, I put out a paper with Ping Gao, where we kind of explicitly implemented that framework in a particular concrete example. And my talk will be primarily based in this second work, but I will be presenting the general framework first. And there's an upcoming work with Daniel and Jan, which has been in preparation for a while. It addresses some important issues which I believe we won't be able to get into today. So I would like to make this, I know that Zoom talks are sort of more tiresome than real life talks, so feel free to engage to the degree you feel comfortable. I prefer this to be more of a discussion. So let me kind of set the stage. The question we want to ask is a very simple one to state. Suppose we're in the context of ADS CFT. So suppose you have a holographic CFT, and let's say, for the sake of this discussion, you're able to simulate in some, you're able to build a system in your lab that simulates n equals 4 super Young fields, let's say. And imagine that you've prepared that CFT in a high energy state, describing in the holographic dual a bulk black hole. This is the black hole here. This is the horizon. Let's say it was formed from collapse of some kind of shell. So the question I want to ask is, suppose now that you have an observer inside this hologram, inside this bulk, originally somewhere outside, close to the asymptotic boundary, and who just is an inertial observer, so he just falls in this black hole ADS. At some point, according to GR, after a finite amount of proper time, this guy will be behind this black hole horizon, and they can measure, let's say, the local value of a field somewhere behind the horizon. So the question I want to ask is, what CFT operator should I, as the experimentalist outside of the system who built the CFT in the lab, what CFT operator can I measure in order to learn about the statistics of the measurements that this guy performed? So what is the CFT dual of this bulk local operator in the black hole interior that this guy will have access to? It's a very simple question to state, but I want to emphasize that this problem is not just a technical problem, it's a conceptual problem. In that currently, at the current level of understanding of this ADS CFT dictionary, there is no definition of this operator in the CFT, of this local bulk field in the CFT. Even if you were able to simulate n equals 4 super Young mills, and even if you were able to perform an arbitrarily complex measurement on it or operation on it, you wouldn't know what operator to measure in order to answer this question about the experience of the infalling observer. So part of our goal, in fact, the first part of this talk is to even define what this operator should be, and then to measure it in a particular example. But we'll put some non-trivial amount of work in even defining the question technically. And now you may ask, well, why is this question so difficult? Why is it so hard to define what this operator is inside the black hole? And there's many answers to this, but ultimately, I think they all come down to the fact that this question is very, very intimately related to the black hole information problem in ADS CFT. And that's why we care, in fact, about the answer to this question. And I want, of course, I would need an entire talk in order to go through all the subtleties of the information problem, but I want to give you a very quick cartoon of it in order to emphasize where exactly this question connects with this ADS information problem, with this black hole information problem. So,
sorry, Lampros.
Yes.
It's just a tangential comment, but are you going to comment on the other proposal that was recently suggested by Hong Liu in France?
So if you want me to comment on that, I can, but I would prefer to do this after I present in my formal.
Sounds good.
And then we can discuss those.
Of course.
I have no other plans for the afternoon, so I can stay here entirely long. Yes, I should say there are a number of other proposals for how to access the black hole interior. First, going back to the work of Kyriakos Papadodimos and Subrat Razou, and their work has been the inspiration for my exploration. There's a recent paper by Hong Liu and Sam Lutherzer, where they also use some interesting tools for addressing the same question. I will argue that both of these constructions have a shortcoming, which I can address in my formalism, but I believe we won't be able to see that shortcoming in detail in this talk. We can discuss this after the main material has been presented first. But I'm happy to discuss this because it's an interesting subject. So here we will take a different approach for this question than the other works. So, okay, first, just to explain for those of you who are not, experts in ADS, CFT, or black hole physics, why is this question so elusive or interesting even? I just want to give you a cartoon of the information problem in ADS to see how exactly this question fits in. So the information problem can be stated in ADS as follows. Suppose that you have a small black hole in ADS below the Hawking-Page transition, which is a black hole that evaporates, like the ones in flat space. The information problem can be stated somewhat superficially, but in essence correctly, by looking at some bulk Cauchy slice that lives at some time much later after the formation, long after the formation of the black hole by the collapse. So what you do there is then you split the system, the degrees of freedom on that slice, you split it into 3 subsystems, spatially separated, so all kind of independent degrees of freedom at the level of the QFT. You have this subsystem A, which is sort of the early Hawking radiation, contains the early Hawking radiation. You have these very near horizon modes, which are the Hawking radiation to be emitted in the future. And you have the interior degrees of freedom, which is the subsystem C, that never escapes according to the semi-classical Penrose diagram, because the horizon is always null, so they can never escape. So the statement then is the following, that if the evaporation of the black hole is a unitary process, which by the way, in the setup it's explicitly a unitary process because we have a quantum description of the theory in terms of the CFT, then the system A and system B form the entirety of the Hawking radiation that will ever be emitted, which means if the original state is pure, then the global state of B and A is also pure, which means A is very highly entangled with B. So purity or unitarity implies that A and B are very highly correlated with each other. On the other hand, if the horizon is a smooth region of space, like the equivalence principle would suggest, this means that if I was an observer that was kind of traveling along some infalling geodesic, then the amount of energy flux that I would measure, let's say, across a little, along a little proper time around this horizon crossing moment, should not be large, right? It should be 0 or some order 1 value. It shouldn't be some sort of divergent energy tensor that would measure at the horizon, if the equivalence principle holds in the set. But to ensure that this energy flux does not diverge, I need a high degree of entanglement between the subsystem C on one side of the horizon and the subsystem B on the other side of the horizon. which means that smoothness, or the equivalence principle, requires C and B to be very highly entangled as well. So what we have now is three subsystems that need to have different entanglement structures depending on coming from unitarity and smoothness. And the statement is that these two cannot go together. Namely, there exists no quantum mechanical state that can support this type of entanglement structure that is required by these two considerations together. That in fact, what you can say, of course, this is a sketchy argument, but you can show that you will parametrically violate a theorem about all quantum states if you require the particular kind of entanglement structure to be true. Okay, so now from this is the kind of the observation, a statement of the information problem. There's all sorts of different approaches that people have taken in order to try to answer it, and we will not play favorites. What I will just point out is that in this particular setup, there is no question about whether A and B are, whether unitarity holds. Unitarity holds explicitly. So the question of the information problem ultimately boils down to actually probing the interior of this black hole, namely to measure, let's say, the stress energy tensor behind the horizon. This is the firewall version of the information problem, and this is kind of what we're trying to do. We're trying to define a CFT operator that can tell us whether a firewall or not exists. That is basically what we're doing. That's why the question of the reconstruction, CFT reconstruction of the interior is related to the information problem, just to give you some motivation for why to care about what I'm about to say.
Sorry, but if you reconstruct, should C and AB be the same, or they are different systems?
A, B, C are distinct if I treat them in the formalism of bulk QFT about this background. But of course, the information problem, one way of kind of avoiding this logical contradiction that we arrived at is to say that, well, perhaps C, B, and A are actually not independent degrees of freedom, and therefore this entanglement argument was incorrect because it assumed that the systems are independent. In fact, this is also what I think the ultimate resolution of that is. But the question that I'm asking is independent of what the resolution is.
But no, because if you have an operator in C, and you say that it's also given by an operator at the boundary, things at the boundary are kind of outside, so are more like AB than.
Yeah. So okay.
You're assuming that somehow.
That is right. Okay, that's an interesting question and a fairly subtle one, in fact. So here we are in the context of ADS CFT, where we take this duality at face value. So we assume that this CFT that lives on the boundary is a complete description of the bulk physics. In fact, it's the UV completion of the bulk physics, which means there is nothing that the CFT doesn't describe. Anything that there is to describe about the bulk is describable in the CFT. Now, as you point out, this clearly is in violation of the causality of along the extra dimension of this bulk. And in fact, we do understand that this causality of the bulk is an approximate feature. Namely, there are simple degrees of freedom in the CFT that are indeed kind of obeying this causal aspects of the bulk, but sufficiently complex measurements in the CFT do not need to conform to this bulk causality. And therefore, this is how, so there are indeed simple operators of the CFT, like the single trace operators, the so-called, the ones that thermalize according to the ETH, only see the exterior of the black hole, and just see some thermal state. But sufficiently complex measurements can actually probe the fine structure of the black hole, and it is some complex operator among this kind of class of complex operators that should describe that interior measure. And we want to identify, we want to find the prescription that will tell us which complex operator sees inside.
Okay, thank you.
I want to emphasize that the information problem is sort of a way stated is a semi-classical problem. It's you arrive at the information problem from analyzing kind of the semi-classical bulk physics, Q of t on curved spacetime. That's when you arrive at the information problem. In holography, the strict information problem is resolved. The question that remains is precisely what is the nature of this interior? What operators describe these degrees of freedom that we semi-classically attribute to this interior region? So that's basically my motivation for this work.
Lampros?
Yeah.
Would you agree with the statement that this argument ignores the fact that this statement that we sort of believe in, which is C is state dependent. All observables in C are going to be state dependent.
Well, I mean, that is a statement that may or may not be true, and also even if it is true, the question is how state dependent is it?
Some level of state dependence must be there because
okay, right, okay. I mean, yes,
I didn't say it's like some level of state dependence is for sure there.
Yes, but you need to so state dependence here you're
let me just clarify. I didn't say that the argument is wrong or anything. I just said the argument ignored the fact that we know there has to be some state dependence.
So, all right. So I did not, I was careful to not make stronger statements that I'm willing to make here. I said there should exist some operators which, given this black hole state, describe the interior. I did not make a statement that these operators describe the interior of all black holes that I could put in this place, or that they're independent of the black hole microstate, for example. So state dependence is somehow included in the realm of possibilities that I'm allowing here. The degree of state dependence is something that we need to discuss, and our prescription, in fact, will be state dependent, and we'll discuss details of that later.
Okay, thank you.
Yeah, so precisely the rules for obtaining these interior degrees of freedom are obtaining the rules is part of the game that we're trying to ask. Is there state dependence? How much of it is there? And so on. Okay, so this was motivation. We're not going to make any more statements about the information problem in this talk. I just wanted to kind of embed this question into this framework for appreciating it. So this is the question, therefore, what CFT degrees of freedom describe these interior operators given a black hole state? Okay, so
sorry, one more quick question. Are you gonna focus on one-sided black holes throughout the talk, or are you gonna comment on the two-sided black hole? Has a little bit of a different story.
Good. So, all right. So the goal of this talk is the following. I will present to you first, a general framework for trying to address this question. This will be for single-sided black holes, for two-sided black holes, for any type of black hole you like. So the first few slides will be explaining the framework in a sufficiently formal and abstract way, but in order to give you some intuition of how it works. And then we will apply this framework in a particular explicit example, which will be a two-sided black hole.
That's great. Yeah.
Okay, so it's good to have this in mind, that I will first give you certain abstract arguments that you may or may not be happy with, but it's in order to build an intuition for it, and then we'll make an explicit computation that confirms that it works in a particular setup. All right, so this is the question we're asking, and here's the very general, we will slowly start now articulating what we're gonna do. So the general philosophy that we will follow in order to access this interior will be the following. We will take a sort of operational point of view. What we will do is that we will introduce an extra excitation into the system, which we will call the observer. Now, this will be a type of excitation with special properties that we will explain in quite some length. And this is what we're going to learn how to do. Now, this observer is some semi-classical excitation that will fall inside the black hole, following some geodesic. So our goal now is to identify the generator of the proper time of this observer, namely the CFT operator that translates degrees of freedom in the bulk with reference to that infalling geodesic, that translates them along that infalling geodesic. So our strategy will be therefore the following. we start with some bulk field somewhere outside, close to the asymptotic boundary and near this observer that I'm talking about. We reconstruct it in the CFT using ordinary CFT reconstruction tools, the Hamilton-Cabot-Lifshitz and Low reconstruction, for example, that allows us to write this degree of freedom as some sort of integral over the boundary space-time of fields of operators in the CFT. We take this as an input, and then we will identify some operator, okay, some Hermitian operator, some Hamiltonian in the CFT, which then, when acting on this phi, translates it along this geodesic, and therefore we can define the interior guy as the evolution of this initial guy. So this guy is a CFT operator by ordinary bulk reconstruction. This is the subject of this talk, and this is a family of CFT operators describing local fields at different proper times along this trajectory, including the interior. This was our goal. So our goal is to propagate this operator in proper time. Of course, you may say, well, at the level of the bulk QFT, you know, if we were just allowed to use the formalism of bulk QFT on top of the background, I know how to do this. I'll just choose some Cauchy slice and a vector field, some psi vector field, which has the right behavior near the probe, and I'll just integrate the bulk stress tensor along this Cauchy slice with the appropriate vector field. That does the job, but we don't want to use bulk QFT because bulk QFT is what leads to the information problem to begin with. We want to find the CFT operator that does the job, and this is our goal.
Lampros?
Yeah.
Here's a very silly question. Why is that operator not the Hamiltonian of the boundary theory?
Oh, the Hamiltonian of the boundary theory is more related to this asymptotic clock, right? It's more related to the Schwarzschild clock that takes an infinite amount of time to kind of take you inside. That is, of course, not a precise statement, as you probably know, but it's the action of the boundary Hamiltonian on the semi-classical bulk fields is this Schwarzschild Hamiltonian. So it doesn't really take us inside.
So then my next question would be that this flow that you're trying to construct, it supposedly corresponds to some sort of a slicing of the bulk that go behind the horizon. What kind of slicing is it?
Well, good. So yes, what you're saying is correct. In the general framework, the most general framework that I will start presenting shortly, this flow will have the right behavior only near the probe. Far away, there's of course an ambiguity in defining what this proper time flow means, and the same ambiguity appears in this formalism. So the action, the operator that we will construct will be a flow that has the right action on this little subset of operators living near the probe. In the explicit example that we're gonna perform in the 2D SYK model, the slicing indeed, because of the simplicity of the model, it extends in the entire bulk, and it's some kind of slicing that kind of goes into the interior. But that's an artifact of the simplicity of the explicit example. Oops.
Okay, thank you.
So something good. Okay.
One more question.
Yeah, of course.
So this operator inside the black hole, does it depend on the observer, or is the observer just a intermediate step?
Yeah. So they depend. So they depend on the observer in that they do depend on the observer, but for the appropriate kind of observer, they are fairly universal. And we will actually see explicitly how this works in the example that I will give. So yeah, remember that this is an important question. Remember it for when we go to SYK and we do the computation. But before we dive into all these details, I want to give you now the framework. How do we do this? How do we start? So here's the idea that Daniel and I used in order to get a handle on this question back in 2020. So this here, I'm drawing a slice of space-time with the black hole in the center, a time slice. So, and this is our observer. And we took our observer to be, imagine that our little observer that we want to use to probe the interior is another black hole, but a small one, much, much smaller than the black hole that we want to fall inside. This red dot here is this operator phi, the original phi that ATM is for atmosphere, in the atmosphere of the black hole, which is the operator we want to propagate inwards. So imagine that we knew how to define, how to prepare that initial state with a big black hole in the center and a small black hole out towards the boundary. Then if I solve Einstein's equations and I evolve the system, well, the spacetime will be looking somewhat like this. It's not a true Penrose diagram, but here's the horizon of the big black hole, and here's the apparent horizon of the small black hole, drawn here as a probe following some geodesic falling in. At some point, there will be, from the outside, there will be a black hole merger happening. The horizon will shift outwards because the black hole got fatter and so on. But from the point of view of the infalling frame, if we were living on a planet circling around this guy, nothing really happens in the horizon according to GR, right? You're in a black hole that's much, much smaller than the big black hole you're falling in. So you're just crossing a horizon, you keep seeing the black hole. So the reason why this setup is useful is the following. Because if my observer is itself, if the probe is itself a little black hole, then it's a natural notion of time in its neighborhood. And this is given by the Schwarzschild clock. Right? The neighborhood of this black hole will be approximately Schwarzschild. So there's a Schwarzschild, a local killing vector. It's not a global killing vector of the geometry, but it's a local killing vector of the geometry. So there's this local killing vector, the Schwarzschild time, that defines the Schwarzschild time. And the important thing is that we know how to construct this Schwarzschild time in the CFT given certain assumptions. In particular, this near horizon Schwarzschild Hamiltonian, when my black hole is in local thermal equilibrium, namely when the small black hole doesn't accrete any mass along its path, then this near horizon Schwarzschild Hamiltonian is identified through ADS-CFT with a particular operator, which is a modular Hamiltonian, okay? And I will explain exactly what I mean by this modular Hamiltonian, first schematically and then precisely. So this modular Hamiltonian is the following. The modular Hamiltonian is defined as minus the logarithm of a density matrix. But what is this density matrix that we use to define this relevant K? So it's the following. The black hole, the probe black hole, is a subsystem of the bulk. So the whole bulk with the two black holes in it is in some state psi. The density matrix of the whole CFT is this subsystem psi, is this projector on this psi state. The density matrix, which we're going to use to construct the modular Hamiltonian, will be the density matrix obtained by tracing out the subsystem, which consists of the black hole, of the probe black hole, this tiny one here. So by tracing out the black hole, we obtain a reduced density matrix of the rest of the universe. And this density matrix, its logarithm, its generator, will be the modular Hamiltonian, which I claim generates this Schwarzschild time evolution. So in very, very broad strokes, and without having explained technically how I do this, I'm about to, without explaining technically how I do this, this is the picture you should have in mind. We have a state describing the universe with black hole and my observer. We remove the observer from the system by tracing out its state, its internal state, and we obtain a reduced density matrix for the rest of the universe without the observer. Well, the modular Hamiltonian for this density matrix is generating the Hamiltonian, this Schwarzschild Hamiltonian that I'm talking about.
Sorry, Lampros. But here you mean by the modular Hamiltonian, not the two-sided thing, not the log of rho minus log of rho of A minus log of rho of A bar. You mean the one-sided thing, or?
Yeah, in this case, I mean the one-sided thing, but you know, there's in the particular technical way that I haven't explained to you how to define this trace over the black hole. This is very, very schematic at this point. I'm trying to give you the intuition. I will explain now how to do this tracing, how to precisely separate the black hole from the system. And in this case, you can think of this modular Hamiltonian as either being the two-sided or the single-sided. You'll see this explicitly in a second. For now, I'm just presenting the essence of what I'm about to do. So it is this. So the reduced density matrix of the universe without the black hole in it is the operator we're going to use to propagate this degree of freedom along this Schwarzschild clock. All right. Well, how do you do this? By the way, this sounds like mysterious, but this sounds a bit mysterious, but there's a very simple version of that. If your probe black hole was the only thing that existed in that universe, it was like some static black hole sitting at the center of ADS. Then the reduced density matrix, after you trace out the black hole, is just a thermal density matrix. So this modular Hamiltonian K, which is minus the logarithm of rho, is just the Hamiltonian normalized by the temperature, by the inverse temperature. And indeed, in that case, the thing that propagates us in Schwarzschild time is just the Hamiltonian of the CFT. There's no mystery in this particular situation. The non-trivial claim I'm making is that the same object, appropriately defined, generates this Schwarzschild time evolution about any near the black hole in any background that this black hole may be embedded in, not just in this very, very simple setup.
Sorry, you're also not talking about this operator in general. You're talking about the action of this operator near the entanglement surface.
Correct. Yes.
So you don't care about how it acts outside, or you don't have
Correct.
an intuition about that.
Correct. No, I do not. There is no. The action of that far away from the horizon is not under control, and we don't care about it much. This is the type of this is the action of the operator on these correlators in the atmosphere, in the neighborhood of the entanglement surface. You're right, and this will be implicit in all the statements I'm making about this. But yes, it's an important side. Okay, so let me now explain briefly how you perform this. How do you separate the black hole and trace it out? What does this even mean? So I will present this formalism first abstractly, and then we're going to go straight. The next step from this slide is to do this explicitly in an example where we can see all the moving parts. But I want to first give you the general idea. So remember, the thing that we want to do is we want to prepare a state with a big black hole at the center and a small black hole out here, and somehow learn how to trace out the microstates of this small black hole to obtain a density matrix. Okay, so let's forget about this guy for a second. How would you begin to prepare a state like this? Well, that's very simple. Imagine that this is your CFT here. Use a different color. You have a CFT over here. This is a time slice of the CFT. And what you see here is a Euclidean path integral that prepares a wave function for the CFT, a state. So you want to put a black hole at the center. So what you're going to do is you're going to act at the origin of the Euclidean plane, of the complex plane. You'll act with some operator with some very high dimension. That's ordinary ADS CFT. Just act with a high dimension operator, and this will create a state, high energy state, which is this black hole. Done with that. Now we want to introduce a little black hole out here. How would you do this? So here's a concrete way for doing this in a way that the rest of the formalism is under control. Let's append a new system to my theory, a system that I will refer to as the reference. So I had my holographic CFT with a Hilbert space, and then a tensor factor, a reference system. The details of this reference are not very important, but take it for concreteness to be another copy of the original CFT. It doesn't matter, but let's take it to be that for the sake of the argument. So now you have the CFT Hilbert space, and you expanded the system, you extended it to include this extra Hilbert space. And in this larger Hilbert space, I will define the following state. You have the Euclidean path integral in the CFT with this heavy insertion, which creates the big black hole. And what I'm going to do is I'm going to act on the two systems here with an operator that couples, or more precisely entangles, the CFT with this reference system. What this is here is a sum of bilocal operators that couples the CFT and this reference system. And what this does is it prepares an entangled state between the CFT and the reference. We don't deform the Hamiltonian of the theory, we just prepare an entangled state between these two systems. So now comes the non-trivial argument. Or trivial, it depends on your predisposition. If these operators here that I'm using, that I'm acting with in this CFT system are in a sufficiently high energy window, the state I prepare this way in the bulk is dominated by the branch of the wave function that contains a small black hole out here towards the asymptotic boundary. Okay. Now, clearly, this is not true if my operators OI are low energy single trace fields. I need these operators that I'm acting with in the system to be of sufficiently high energy. They have to have energies that are comparable to n squared. But the claim is that if I adjust the width of the energies from which I'm picking these operators from and its average energy appropriately, then this state over here in the bulk describes a black hole of sufficient of the mass that I control by controlling the energy width of the operators that I'm summing over. This is just a statement about the thermodynamic dominance of black holes over other states. Namely, if the thing that you're acting with is of sufficiently high energy state and has a sufficiently narrow width, then the configuration that will dominate in the bulk will be the one that's entropically favorable. And for a particular parametric regime, this is the black hole configuration. So it doesn't matter exactly what I'm doing here, as long as I'm doing it in the right parametric regime of energies. And that would be a black hole.
Sorry, Lampros.
Yeah.
So you're gonna pick the dimension of these operators OI to be n squared, but epsilon n squared, is that what it is?
Yes, they're gonna be n squared, but it's gonna be a small fraction of n squared.
So epsilon delta.
Yeah, that's yes, that's right. Yeah. Mm-hmm.
And then you mean sum over, so in that your sum over I runs from 1 to n, you mean n of the super Yang-Mills, or you mean?
Oh yeah, I know. This is summing over all operators in let's say in this particular energy window. Yeah, this is.
What is the width of the window?
Oh, okay. So yeah, good. So there are a number of statements that one needs to make for the average energy of that window and the width of the window in order for the black holes to be thermodynamically dominant and so on. So, so the width of the window will have to be much larger than order 1, but much smaller than order G Newton to the -1/2. So the width of the window must be much larger than 1, but much smaller than G Newton to the -1/2. So this is important, both of these. So it has to be a sufficiently large, but not too large energy width. And then you can show that this state will describe black holes smaller than LADS, by the way, for a parametric regime that I'm happy to describe. I have a slide about this afterwards, but I don't want to get into that detail for now. For now, just take my word, and I can explain it afterwards, that for an appropriate, there exists an appropriate choice of the window from which to select these operators, which allow me to build which allow me to construct a black hole here, whose size I can control, and I can make it smaller than LADS.
Maybe I can ask one question a little bit differently. What's the dimension of this microcanonical ensemble you're considering?
What's the dimension of the micro?
Yeah, the number of vectors that you include in there, orthogonal vectors.
It's gonna be e to the s.
E to m squared, right?
Yeah, right. Something like that.
Okay, so it's e to m squared. Good. Thank you.
No, this don't take this end. This end was incorrect. It was came from some copying and pasting. That yeah. Okay. Right. So so what we did now. So I understand that this is a fairly formal argument, but I can make this precise. I mean, I've already told you that how to make this precise, but I can discuss the details at length. The point is that in this preparation, we have constructed a spacetime with a big black hole at the center, a small black hole over here, and importantly, the microstates of the black hole are highly correlated with this reference that I appended. So now what we do in trace out the black hole, we simply trace out this reference and obtain a state, a mixed state now on the Hilbert space of the original CFT. And this is the there's a density matrix on this CFT Hilbert space, and this is precisely the density matrix that I'm using to define the modular operator I care about. The claim is now that this K, defined in such a way, does the job that I'm telling you it does. That it propagates me along the proper time of this guy. Okay, now at this point, you may have believed me, or you may say, well, okay, this sounds like a very formal argument. It's probably impossible to make it work practically in any example that I care about, so I could care less. Well, this is a totally justified feeling if you have it. So my goal from this point on is to actually do all this explicit and compute that modular flow defined in this way, or in a very closely related way, and show that it does work in an example where we can do the computation explicitly. So this is my.
Sorry, I'm a little confused. So you trace only the reference and not the black hole.
Well, the way we prepared the black hole, you see, you can think of each of these operators that I'm acting with in the CFT system as a microstate of that small black hole. So here, because of the way I'm acting with this operator, every microstate is correlated with a particular state of the reference. So by tracing out the reference, it's kind of declaring ignorance about what microstate my pro-black hole is in. I
understand that, but what I'm asking is this: the density matrix for which you take the log of, is this a density matrix of the boundary CFT, or is it the density matrix of the? But you previously said it's a density matrix of the boundary CFT with something removed. Yeah.
So the problem. So this is the intuition that I want you to have about what this procedure achieves. So it is. You could imagine building the black hole without ever talking about the reference, and then you would have to do what I was describing earlier. You would have to identify somehow the subsystem of the CFT that corresponds to the small black hole. But that is very, very difficult to do. So we're making a strategic retreat and say, well, one way of introducing this black hole into the system and tracing over its microstates is to introduce it in this way, to somehow introduce it entangled with
I see. So this is actually, it's like a log of an actual density matrix. There is no subtlety regarding that. This is an honest agreement density matrix of the boundary theory. Thank you.
That's right. Yes, precisely. So this avoids a myriad of technical problems in defining the reduced density matrix like I described it heuristically earlier. This is a step for avoiding all sorts of technical issues with defining the modular Hamiltonian as I described it before. But conceptually, it's the same thing. You're tracing over the microstates of this black hole. I think this is fairly intuitively clear by this picture. But we can also do computations with it. So now, good. So now let's actually try to do this. Let's actually try to to construct this guy. And we'll do this in a concrete example in 2 dimensions. So in 2 dimensions, there's a toy version of this holographic duality. Correspondence between a dilaton gravity theory in 2-dimensional anti-de Sitter space called Untitled theory. Here's the action just for reference. And this dilaton gravity theory, its dynamics, is supposed to be dual to the dynamics in a low energy sector of a pair of quantum mechanical systems called SYK models. And you may say, why a pair? Well, the ADS2 geometry has 2 asymptotic boundaries because it's 2-dimensional, has 2 asymptotic boundaries. So we have 1 quantum mechanical system for each of the left and the right asymptotic boundaries. And the Hamiltonian of this pair of SYK models is, is decoupled. So the left and right systems are decoupled from each other, but each of them is a strongly coupled quantum mechanical system. In particular, each of them consists of a bunch of Majorana fermions. There's n of them, where n is taken to be very large. And they're coupled together in batches of Q fermions together, but all of them, with couplings couplings J, which are taken to be Gaussian random variables. So we just draw them from some Gaussian ensemble with 0 average and some variance that we control. So this is the each of these systems is a maximally chaotic theory, quantum mechanical system, and together in about a certain state, they describe the physics of this dilaton gravity theory about ADS2. So the important thing is that there exists a black hole state in this SYK system. In particular, this is the so-called thermofield double state between the left and the right system. What this thermofield double means is that here these are energy eigenstates of each of the quantum systems. You take a very delicately entangled state between left and right, where these guys are correlated, energies are correlated between left and right, and they come with a thermal weight, the Boltzmann weight. And the phases are fine-tuned to be 0. So this is a special state in the quantum system. There's a number of ways of representing it. You can think of this as taking the maximal entangled state, the maximally entangled state, and then acting on it with some amount of Euclidean evolution with respect to the Hamiltonian, let's say, of Dirac. It's clear then that this guy will indeed give you this. And it's also convenient to represent this as a path integral, some Euclidean evolution preparing a wave function at this t equals 0 slice. Now, from ADS-CFT, there's a dual dilaton gravity wave function, which is sort of a Hartle-Hawking wave function. The state that this, the configuration of the gravitational theory that this state describes is a 2-sided ADS wormhole. What this means is that it's a geometry that is locally everywhere ADS2, but we see it from the perspective of 2 ADS2 Rindler wedges. So you have the left wedge and the right wedge, and the SYK Hamiltonians, the SYK systems live on these 2 asymptotic boundaries. This is SYK left, SYK right. So there's a state I prepare between the left and right, which describes this kind of space-time geometry. And this is a type of black hole in that each of the SYKs is only causally sort of connected to the exterior wedge, but geometrically there exists an interior that you can access. This interior is precisely this 2-sided black hole we want to fall inside and look at its interior. All right. So this is our setup. This is the analog of our holographic CFT, and this thermofield double state is the analog of our high energy state that describes the black hole. This is the black hole we want to jump inside. And now we want to implement this fairly abstract formalism that we developed in order to look inside. So what we're going to do is the following. Let's say that you wanted to add a particle on top of this configuration. Well, you would know what to do. Then all you have to do is you go back to this Euclidean preparation of the initial state, and somewhere along this boundary arc, you insert an operator. So you can choose where to insert this, and there's two arc lengths that you need to determine, which are called here better right and better left. So this tells you exactly where along this circle you introduce. And once you act with this, you may say, what does the state describe? Well, the state in the box that this thing describes is you introduce a particle here which will follow a geodesic. So in this piece, the geodesic is Euclidean, and then it will be some Lorentzian geodesic that falls inside. This is just a single particle added on the black hole state, and the state looks kind of like this. But now we want to do something more complicated. We want to introduce an observer like we were doing before. So what we have to do now is we will follow the same kind of formal procedure we did before. We will append the reference system. The reference system for concreteness will take this to consist of n Dirac fermions. These guys. And then what I will do is I'll have the same kind of Euclidean preparation on the system. I will initiate my reference into the vacuum state. And then what I will do is that I will act with a unitary U that couples my system somewhere along the Euclidean evolution, couples the system to the reference. This will create an entangled system, a state between left, right, and reference now. And this unitary will take it for concreteness to look like this. It is generated by the sum of these guys. These are the Majorana fermions of the SYK system, and these are the Dirac fermions of the reference system. I could have chosen many different couplings, but I choose that for simplicity, and I'm leaving one parameter undetermined, this alpha, and this alpha controls the strength of this coupling, which controls the amount of entanglement that I'm introducing with the reference.
So, sorry, Lampros, do you mean a unitary over there, or is that a Euclidean time evolution?
Well, this guy here is a unitary because of the anti-commutators between psi and chi, but it's introduced along the Euclidean evolution. So I'm not acting with a unitary on the state. I'm inserting a unitary. Yeah. Is
this going to play an important role for you, or is it just that you want to prepare? You want to just take an entangled state of the SYK of this yeah, you just. Does it matter how you prepare the state?
Doesn't matter how I interpret the state?
Prepare that state, entangled state with the reference.
So I don't think it matters much, but this is the only, well, I wanted to do it as, I hope it's clear that this is sort of the closest analog to this higher dimensional general discussion we had earlier. This is kind of, this is how we prepared our black hole state in the higher dimensional situation. And here we're making this explicit by choosing, by choosing this coupling between the system and the reference to be a very explicit coupling. It doesn't matter that I prepared the entangled state like that and not in a different way. I don't think so. But there's, I've only done the computation for this particular preparation, so I'm open to the possibility of subtleties I haven't appreciated.
Okay, thank you.
Okay, so yeah, so this is kind of an explicit realization of what we did before, where everything now is explicitly written down. We have a precise equation for the state expressed in terms of the microscopic degrees of freedom. So going back to what we want to do, remember the reason why we're doing all this is because we want to take some Bok field and translate it along this geodesic that our probe will follow in the Bok. And the claim was that if I trace out the reference, it's equivalent to well, it will give us a reduced density matrix for the left-right system. And this reduced density matrix will define this modular flow. And the claim is that then somehow this actually ends up translating us along this geodesic. So what we did was actually we saw this explicitly in our formulas. So here's the statement that came out of the computation I'm about to describe. The statement is the following, that what the computation shows is that in an appropriate parametric regime, which I'm happy to discuss in detail, if you take some initial bulk fermion, which you have reconstructed on the boundary in terms of the Majoranas, and then you use that modular Hamiltonian to propagate this guy, you construct a one-parameter family of operators, this chi rho of S, and this one-parameter family of boundary operators corresponds to this one-parameter family of bulk fields that live at the same distance from the geodesic of the probe as the initial guy, but translated along the geodesic by some proper time tau, which is related to this modular parameter S by some conversion factor, which is an effective temperature, an effective inverse temperature for this probe that we introduced. So the computation I'm about to illustrate shows that when this modular flow constructed in this way, where you bring the reference, you entangle it in the way we described, and then you trace it out, the modular flow between left and right obtained this way acts on a bulk fermion geometrically. It keeps its distance relative to the probe geodesic fixed and translates it in proper time. That is what this diagram here says, with a precise correspondence between the geometric parameter of proper time and this modular flow parameter S obtained from the calculation. This is a statement.
Sorry, I'm understanding this correctly. You keep calling this a modular flow, but it's really like just a Hamiltonian on the boundary field, right? It's just some Hamiltonian on the boundary field.
Well, it's the modular Hamiltonian for my system after I trace out the observer, right? After I trace out the
modular Hamiltonian with respect to the reference. I mean,
yeah.
The reference that you added by hand, it added that. I mean, I can any Hamiltonian I pick on any generator one parameter flow I define on some sort of a CFT or something. I can use a reference and say, oh, I interpret this Hamiltonian as a modular Hamiltonian.
Yeah. That, I mean, of course, yeah, you can always do something like this. I agree with you. The important thing is that the important thing is that the only information that I need to specify is the initial state. How I prepare the initial state. The initial state determines the dynamics as seen from the reference frame of that probe. That's the statement I'm making. I'm proposing a physical identification between the time experienced by an internal probe and the modular Hamiltonian associated to this particular in the modular Hamiltonian for that subsystem in that initial state. That is the statement I'm making.
Sorry, I'm very confused now. Right. Let's say I just put the system and the reference in a maximally entangled state. So let's say my reference has finite dimensions.
Yeah.
I put it in maximally entangled state. Now the reduced density matrix is just the identity operator.
Yeah, in that case, it's trivial. Yeah, you're right.
So what is the flow that we're talking about?
Well, yeah, okay. So let's perhaps it's useful to keep in mind what the underlying physics here is. You want to define an internal clock in the CFT, a clock that is not the n equals Fermions Hamiltonian, which is sort of the asymptotic clock. You want to define an internal clock. To define an internal clock, you need to somehow identify a subsystem with a large number of microstates, and you need this different microstates to be weighted by different weights so that you can distinguish them between them. And this allows you to define a notion of time. If you put all these microstates to have the same weights, then there is no natural kind of, as you say, it's just the identity operator. So this construction just breaks, doesn't apply. The statement here is that with the way I'm proposing is a way of identifying an internal a Hamiltonian for evolving the system, which depends on two things: the initial wave function of the universe and the subsystem that I want to use as my reference frame. And this is what this prescription is supposed to do. Two inputs, right? There's a system. I have defined my system. I have chosen my initial state, and then I've chosen the subsystem that I want to use as my frame of reference. And the claim is that if you choose the frame of reference appropriately, the modular Hamiltonian is identified with this flow.
Thank you so much.
Sorry, was that thank you, or was that?
No, you did answer the question.
Okay. Right. And that actually brings me to the point I want to really emphasize. I haven't shown you why this works yet, and I'm about to give you a couple of details, although I'm running late, and I probably should wrap up soon. But the statement I want to emphasize, which I think is the most important thing, is the following. This is a very simple setup, and there's multiple ways of looking inside behind the black hole, the horizon of this particular black hole. There's all sorts of ways and constructions that people have proposed, and they all work. So the interior of this black hole is not a big mystery. So the reason why we are excited for the fact that this formalism works in this case is because this entire computation is entirely phrased in the SYK. There is no direct reference to the bulk. The only input from the bulk is the reconstruction of this initial bulk operator, this fermion chi at one moment in time, just one input. And then all you need is the initial state of the SYK fermions and the choice of observer, which was precisely this kind of procedure of entangling your CFT or your SYK here with this reference. With these inputs, you identify a family of operators. So this uniquely determines, if you like, a family of operators which are probing the interior. So we're probing the interior directly from the SYK, not from some. There's no input from the bulk other than that. So I don't have time to explain the details, and I think I wanna get to the punchline of this talk, and then I'll wrap up. I need 2 slides, if you allow me 3 more minutes. So the way we compute this is the following. If what I'm saying here is correct, namely if this modular flow does what I'm saying here it does, then I should be able to do the following. I should be able to take this initial chi, modular flow it, and then compute the anti-commutator with some left operator, some operator in the left exterior, chi left. Anti-commutator because we have fermions. So what do we expect if my prescription works in this case? What do we expect? What we expect is that this anti-commutator is 0 for as long as this modular float guy remains space-like separated from chi left. And we expect to spike the moment we cross the light cone, and then just stabilize to some order 1 value. That's what the bulk expectation would be if this family of operators defined by modular flow is the correct one. So this is a very non-trivial thing, because this is a purely SYK computation that's supposed to probe this causality of the emergent spacetime in the black hole interior. So Bing Gao and I set out early last year to actually do this computation explicitly and see if that works, because it's not guaranteed at all. And after 10 months of wrestling with that computation, we actually managed to make it work. So this is the output, and let me actually explain what you're looking at here. This is sort of the punchline of the talk, so let me explain what you're looking at here. So what you're looking at here is a plot of the expectation value of this anti-commutator that probes causality, the causal effect of the left operator on our modular float guy, as a function of the modular time, which is the proper time along this infalling geodesic. And you see three curves, a blue, an orange, and a green. These correspond to the same computation, excuse me, where the left excitation is introduced at a different distance from the boundary, from the horizon. So the blue signal arrives, hits my infalling observer first, the orange is later, and the green even later. And what you see here is that this remains small or zero for an amount of time and then spikes at a particular moment in this proper time. Now, I am showing you a plot purely for dramatic effect, because this anti-commutator can actually be computed analytically in a particular approximation scheme that we employed, which we checked for consistency. So, I could have written down the precise analytic expression for that anti-commutator, but I don't, because it's less illuminating than the plot. You can actually compute the precise moment at which the spike occurs, at which you cross the horizon, and it matches exactly with the expectation from the book. And to connect to the question that Mudassir asked earlier, this result is universal in that it actually doesn't quite depend on the details of the coupling we introduced in this preparation of the state. It doesn't quite depend on the details. The only thing that ends up depending on the details is this effective probe temperature, which kind of set the local clock rate. All the information about the UV details of my entangled state are hidden in one parameter, which you can compute in SYK. But given this one parameter, once you fit that one parameter, everything else is exact. Now, this is comment number one. Comment number two is the fact that this computation doesn't work for any size of the probe. And that kind of connects to Nima's earlier question about the maximally entangled state. And I will explain it in words. I have technical slides, but I don't want to tire you too much. If the entropy, so remember that our observer is introduced by preparing our black hole state and then entangling our SYK with this reference. This entangling introduces some entropy into the system. If the entropy I'm introducing in the system is very, very small, this means that the reduced density matrix, when I trace out this reference, is of very low rank. So this means the modular flow in this case is fairly trivial. And indeed, we see it here that when you make the entanglement very small, the modular flow kind of degenerates and doesn't have this nice behavior here. It just, this behavior kind of gets washed out. A different but similar breakdown happens when you take the entropy of this excitation to be very, very large. When you take the entropy of the excitation to be very, very large, what you end up doing is you decorrelate the left and the right. So you have this black hole supported by the left and right SYKs. You introduce some entropy with the reference, but if the entropy is very large, what you end up doing is that you decorrelate left and right. And therefore, there is no shared interior anymore. And this plot again breaks down. The computation breaks down and you don't get this plot. In fact, this latter breakdown, you can explicitly see it from both breakdowns, you can explicitly see it from the Bok path integral. This breakdown here is a sort of Hawking-Page transition in this ADS2 geometry. I don't have time to explain it, but I'm happy to discuss it if you have questions. The point is that there is a parametric regime of intermediate probe entropies where the modular flow is universal and it exactly matches the expectation from this proper time translation picture in the book. And that's sort of the punchline. This is a signal, this is detecting a signal in the interior of a black hole from a computation that is purely performed in the SYK model. So this is, yeah.
Finish. Sorry, I interrupted. Oh, okay. So so here in this plot, to see a sharp transition, supposedly you've taken n going to infinity, right?
Yes.
So which means that probably you're taking s to go like log of n. Is that right?
No, the amount of
This
time
is-
the amount of time it takes to see to the amount of proper time it takes to probe the interior is order 1. It's not log n.
Oh, I see. So and it's a, but the SF probe is here. What order and is it?
Oh, the entropy of the probe, you mean?
Yeah.
Oh,
Is it n squared
entropy of the
or?
probe. Give me 1 second. One second. The thing, so yeah, so the most kind of clear order parameter is this. It's another parameter related to this alpha. The strength of the coupling is a more is a clear order parameter. So I have the so. So this S is not of order n.
It sounds like n squared.
This S probe, well, here the number of boundary degrees of freedom is n, not n squared. So
Yeah.
this S probe is not order n. If it's order n, then you're in this phase where you break down the entanglement between left and right. So it has to be less than order 1 and much larger than order 1. There's a precise critical entropy at which you get a transition. The thing is that I don't remember the exact formula right now of the entropy. I'm remembering the critical coupling at which the transition happens.
Why can't it be epsilon n?
Yeah, I believe it's I believe it's not epsilon n. I believe
Okay.
I believe the entropy is let me get back to you on this because right now I can tell you the critical coupling of entanglements is related to beta j over q squared. So you have beta j is the coupling of syk, which is taken large, and q is the number of fermions that appear in the coupling of syk, and the critical coupling is at which this transition happens is at which the prescription starts working is supposed to be this ratio. So it's large but not too large. This translates to a particular expression for the probe of the entropy at this location, but it just the formula right now escapes me. So I'm happy to tell you afterwards.
Sure. Well, one more question. So if you said you have analytic expression for that plot that you showed. So
yes.
You have control on looking at what it looks like when n is large but finite, so how it's smoothed out.
Oh yes, good. So that's a good question. So in order to compute this expression, one needs to work in a particular approximation. Of course, you can't solve the SYK equations. This is a fairly complicated setup. So you have to work in certain approximations. So the approximations in which we get the analytic result is n goes to infinity, beta j much larger than 1. This is the coupling of the SYK. Q, we work in large Q, in particular to first subleading order in 1/Q perturbation theory. And we also, as I explained, in order for this to work, you need to take the coupling to be sufficiently large, but not too large.
So sorry, this is not then the usual Q equal 4 SYK. This is large Q.
This is large Q, yes. That's large.
Okay. Yeah, sure.
So these are the sequences of approximations that we make. So all these approximations are necessary in order to get this. And you can ask, for example, and all these approximations are necessary. So this large beta j limit is actually an interesting limit because this is the limit that you have to take in order to get the holographic description of SYK. And you may say, well, how does the result behave once you go away from the infinite beta j, from the very large beta j, once you include 1/beta j corrections? And it turns out that this has the effect of sort of smoothing out this thing, these spikes. Now, quickly you kind of, if you keep moving beta j away from, if you start including subleading corrections of beta j, you quickly leave the regime of validity of this computation. So you can't trust this computation too far in this beta j parameter. But you can see how the computation starts being deformed away from the infinite beta j limit, which is you start seeing these spikes smoothing out. Which so this is one of the things that you can do by playing around with the solution.
Also, do you mind saying again what's alpha?
Alpha was, remember, in this preparation of the state, we acted with this operator that coupled the left-right SYK system and the reference. And this unitary was taken explicitly to be this this coupling between the Fermions and the Dirac Fermions. And alpha was the kind of coupling that was controlling the amount of entanglement I'm introducing in the system.
Yeah, so it basically controls the entropy.
Exactly, yeah. But yeah, that's why when I was giving you earlier the transition point, I was thinking more in terms of this alpha parameter because it's the one that explicitly appears in the various formulas. But I don't have the formula of the entropy in my mind right now.
Thank you.
Yeah, so in short, for a particular, if for an observer that has a large enough entropy, if its prescription works, it's universal, and it matches the bulk expectation from this proper time translation, and it allows us to peek in the interior of this two-sided black hole in SYK. So, and this sort of wraps up my talk in that we set out to construct a purely holographic formalism that would allow us to peek inside the interior of a black hole. And I believe that I hope at least that I convinced you that by this method that I described, which introduces the observer and constructs this modular flow, it seems like you are able to do this. And I gave you a formal argument in the beginning in terms of this black hole setup, but most compellingly, I think I can perform a computation where all the moving parts are understood, and it seems to be working. There's lots of work to be done in order to truly address the information problem, which I kind of motivated the whole talk with respect to. But this is, I think, a partial but non-trivial victory, and I'm happy to share it with you. There's all sorts of things that I could talk about here, but I will just end by saying that I view this as sort of a framework for emergent time. What I described to you was, I gave you a prescription for how to associate the notion of internal time in this kind of quantum gravity system. You chose a subsystem you care about, and I gave you, this subsystem has a notion of time from the bulk point of view. It's the proper time in the reference frame. And I gave you a quantum mechanical way of thinking about this time as the modular time coming from the quantum correlations between your observer and the rest of the universe, which we tried to make it concrete by introducing some technical tools. So a question that, of course, excites me and interests me is whether this is truly what time is all about. You know, whether this is an actual framework for the type of time that we experience in general, in cosmological spacetimes and so on. This is an interesting question. I don't know the answer to that, but I hope that it's a first step towards answering that question. And with that, I will end, and thank you very much for your attention.
Thank you so much for the wonderful talk. Are there questions for Lampros?
I already went half an hour overtime, so I think
that was great. If you don't mind, we're going to keep you a little bit longer.
Oh, I'm happy to stay here. As you see, I have 50 slides in my presentation. I was too ambitious.
All right, I'll let people ask their questions. Are there any questions first? Yeah.
I have a calculation questions.
Yeah, of course.
Why choose Dirac fermions for reference? Why not just the Majorana fermions or SYK, another SYK model?
Oh yeah, you could have done all sorts of different things. We just made that choice. As I stated a couple of times, the details of the reference don't matter because we end up tracing it out. You could have chosen some other system. It could be it's just that this particular system was the one we chose and did everything explicitly. But the details don't matter. In the end, the computation doesn't seem to depend on any of the microscopic. In the parametric regime where it works, the details don't seem to matter much. In fact, we suspect where this universality comes from, actually, and that's probably important to state. In the regime where the computation works, this modular flow that we obtain coincides approximately with an SL2R flow. So this modular Hamiltonian ends up approximately acting like an SL2R generator in this parametric regime where the probe is at intermediate entropies. And of course, this SL2R symmetry is, we know very well by now that it's emergent, it's not built into the theory, and it's related to the maximal chaotic properties of the SYK. So there seems to be an interesting interplay between the maximally chaotic dynamics of this holographic system and the universality of the modular flow, which is important in order to really associate it with the proper time flow, which is itself universal. It's geometric. It acts the same way on all operators. So there seems to be an interesting piece of physics here explaining kind of more microscopically why this modular flow is so well behaved in the setup. And I believe this is the key for the validity of this prescription in higher dimensions as well. And also this closely relates to the question that Nima asked in the beginning. What is the relation between this work and the other approach recently discussed by Hong and Sam? The universality of this modular flow and its connection to this SL2R, the emergent SL2R symmetry, is directly related to, is what ensures the consistency, if you like, of our approach and their approach in this setup. I can discuss about this more, but this is an interesting point that is, I think, physically important.
I have a question. This might be I still don't have a clear statement, but clear question. But so some time ago, you wrote a paper about modular chaos, and in that paper, at the end, you tried to show that by studying the modular chaos, how the Poincare symmetry or Poincare generators emerges. Do you think this relates to this statement that you're saying, like emergence of SL2R?
Right. So excellent. So this paper I wrote with Jan about modular chaos, I mean, it's sort of the prequel of the paper that Hong and Sam wrote about the modular inclusions in the black hole interior recently, in the sense that what they're trying to construct, I mean, they're making, of course, the discussion more explicit, and they inform the discussion in a very interesting way. But what in essence, what they're doing is they're trying to construct this sort of modular inclusions and from them obtain the modular translations that can shift you into the interior. Well, I mean, that's essentially what Jan and I were doing in a kind of less ambitious setup, but we were explaining how maximal modular chaos is what allows you to define translations that move you outside an entanglement wedge. So that's effectively what they're doing, is just that they make it more explicit. And of course, I've been reading their work very closely. So this approach here is distinct from that other approach that Jan and I started talking about back in 2019. It's distinct technically, but both of them are kind of merging precisely because, as you said, because of their connection in both cases to this emergent SL2R in this case. So this universal modular flow ends up being controlled by the SL2R symmetry, and the modular translations or these modular scrambling modes that you would obtain from the other point of view would also be generators of this SL2R symmetry in this particular setup, right? Where in higher dimensions is more complicated, but in this particular setup, it would be exactly that. So I think that's how all approaches kind of meet in this case, even though the starting points are very distinct. We have a very, in this modular chaos story, you try to define some sort of flow that maps the algebra of one causal wedge to the algebra of another causal wedge, which is modular. Here we have a less ambitious goal. We're trying to say we want to define some operator, and we want to move operators are near my observer with reference to a particular word line. So it's a more local reconstruction what I'm constructing here.
I see. Thank you very much.
It will vary. By the way, I should say that this is an interesting question. I don't know the full answer to that precisely, how these two formalisms meet and in more general. In this case, I understand it because it's a very simple setup, but in higher D, I think it's an interesting question to ask.
Okay.
I have plenty of questions, but I'll wait for other people to ask questions first.
Of course, yeah,
Are there any other questions? If not, let's thank Lampros again.
Thank you for your attention, guys. It's been fun.
We'll stop the recording here and then we go off with our
Okay,
discussion.
so we're offline now. Okay.
Yeah.